Okay, so today we're going to be looking at improper integrals. And the interesting thing with improper integrals is that we're going to explore a little bit about FTC2. So up to this point in the course, every time we have looked at doing a definite integral, we have used FTC2 and we haven't really given it a second thought. Okay, we always just find our antiderivative g of x, and then we can do g of b minus g of a, and that's given us consistent results. So fine. However, what we're going to look at today is what if we can't use FTC2? So what are the situations in which FTC2 would actually fail? Well, if you look a little bit closer at FTC2, the first thing you'll notice is that in order to apply FTC2 in the hypothesis, the first thing is that we need to have a continuous function. The second thing is that it has to be continuous on a closed interval. Okay, now these two things we've sort of taken for granted so far, but that's because every function that we've looked at has satisfied these two conditions. So today we're going to look at the first type of improper integral then. And really that comes down to what happens if you do not have a closed interval. So let's take a look at an example. If we start off here with the integral of 1 over x squared, and we're going to be looking at the area underneath this function from 1, x equals 1, until x equals infinity. So here we don't have a closed interval. The interval that we're actually looking at is going to be from 1 all the way to positive infinity. So first off, let's take a look at sort of how to visualize this. So we have our curve here, 1 over x squared. We want to do the area from x equals 1 and all the way to x equal to infinity. So this green region that you can see here, this is very much what we're talking about. We want to know what is the area of this region. Okay, what's the area between our curve and the x-axis from 1 to infinity. Now, the first thing when you see an interval like this and you see a region like this is that you're likely going to tell yourself, okay, well, the interval width is infinite. You know, we're going from 1 all the way to positive infinity, so the area then of this green region should be infinite. And that makes sense, okay, at first. However, let's go and take a look in this situation as to what this integral actually gives us. So, how do we evaluate the first type of improper integral? So this is type 1. So here we have our curve, 1 over x squared from 1 to infinity. And again, when we look at it, cannot use FTC2 because of that infinite interval. So the first thing we're going to notice is that what if we didn't have to integrate all the way to positive infinity? Okay, we know that we're able to use FTC2 on any closed interval. So what if I started still at x equal to 1, but now I'm going to stop over here at some other value, let's call it x equal to t. So really what I would be looking at is this region right here. And if I were to evaluate that red region, there would be absolutely no issue using FTC2. So fine, let's see how we can utilize that. If I go back to our definite integral, I want to do the integral starting at 1 and going all the way up until t, area underneath 1 over x squared. Fine, except that these two things here are not at all going to be equal to each other, not as is. What we would like to do is go back to our setup here. We know that no matter what the value of t is, we're able to do FTC2. So what if I take t and I increase the value of t? Specifically, I know that the larger the value of t gets, the closer the area of this red region gets to be approximating the area of the green region. And so specifically what I would like to do is take a limit. I would like to take the limit here as t approaches infinity. Okay, and this is how we're going to evaluate this first type of improper integral moving forward. If I replace here my parameter t, or sorry, if I replace my parameter infinity by t, then what we're going to look at doing is the limit as t approaches infinity of that definite integral. So there's sort of two steps to this now. The first one is that we evaluate the definite integral. The second one is that we evaluate this limit. Okay, so the definite integral is not an issue. I leave the limit alone for now. I do the antiderivative 1 over x squared, so that's x to the negative 2. The antiderivative will be negative 1 over x, and I'm going to evaluate that from 1 until t. Fine. Let's now use FTC2 because we know our function is continuous on that closed interval. And using FTC2, I get negative 1 over t minus, and we have to be careful here with the negatives, it's going to be minus negative 1 over 1. So this is what I have, and actually, if we look at it, we have a double negative here on the second portion, so that's fine. Really, we end up with a limit as t approaches infinity, and we're going to have just negative 1 over t plus 1. So here, this limit is actually not too bad at all. As t goes to infinity, what happens here to our 1 over t term? Well, that's going to approach 1 over an infinitely large value. That's going to approach 0. So this whole limit actually exists. This whole limit is just going to be equal to 0 plus 1. It's just going to be equal to 1. So really, what we have now determined is that green area, back over here in Desmos, that green area is actually equal to exactly 1. So you are likely there wondering, how is this actually possible? We've just shown that the area underneath this curve is 1, however it's pretty clear that the base width is infinite, so how is it that the area is not also infinite? Okay, and this is not actually that unfamiliar. If you guys remember back from Cal 1 when you were doing indeterminate forms, you had the indeterminate form 0 multiplied by infinity. Okay, and this is one of the ones that you studied early on, and really this is very much what is happening here with the integral of 1 over x squared from 1 to infinity. We know that the base width is going to be infinitely large, however we also note that the height is going to be approaching 0, and what there turns out to be is a struggle between the two of them. Ultimately, the question is this function 1 over x squared approaching 0 fast enough to cause this integral to not be infinite? And the answer, as we just saw before, is definitely yes. 1 over x squared does go to 0 fast enough for this integral to be equal to 1. Now that concept of being fast enough is one that we're going to talk about. But first, let's take a look at one more integral.